Okay, this is the sort of payoff lecture in the sense that we're going to put together in this and lecture 21 the spectral decomposition of the O monster, the octahedral symmetry, the octahedral cubic symmetry. And today we'll see some applications of it at the very end. But the hard part of this particular lecture is we're going to see the coset space, a description of state vectors and things like that, but mostly we're going to be talking in terms of projection operators that have been split from the class operators. So today we're going to get all of our physics out of just the diagonal projection operators, the P T1 XX or something like that. The next lecture will consider the cases where those numbers are different, and of course that is the real structure of this. But I thought it would be a good idea to look just at the diagonal matrices, D T1 XX, for example, that goes with the projector of that same name, and get a lot of physics that way if the local symmetry is the kind that you want, if you've picked the right kind. So we're going to be calculating, and it's going to be a page full of arithmetic to get these things, but I'm going to expose the arithmetic completely, so that's why it'll take up a whole page. After you get used to this, you can just go with the calculation more efficiently. But that's why I'm taking the time here to show the development of these projectors before I actually begin calculating, and there's some developmental work that only you can see when the actual calculations are being done. Now before we go, all of this is based on having subgroup chains. The pathway through that zoo of crystal groups is many and varied, and the physics of each of the different paths is different as well. And this procedure of nailing the operators that you need to perform projection is really important. So we're going to spend a little bit of time, again, mostly reviewing, but also showing some of the new ones that are associated with the group OH. And we'll be using pieces of this in the third part of the lecture here, where we just consider one type of induced representation in great detail, and use just three of these projectors that we calculate in the second part of the lecture. And I think that this part of it right here will begin to clarify for you what the induced representations are, why that Frobenius reciprocity theorem, which is, I admit, a little bit of a hurdle for someone getting started on this sort of theory. But the other thing I should point out is this is the first lecture where we're really talking about stuff that is brand new and unfinished. So, well, there'll probably be more than the average number of typos on this page, although I've tried to keep that at a minimum. I'll end again here with some aspects of the molecule SF6, the only molecule, or the only type of molecule that really makes a three-dimensional coordinate system with its own structural makeup. A Cartesian molecule, if you will, in 3 dimensions. So let's get started. The thing that we did last time, and a little bit the time before, was introduce the octahedral symmetry either as a cube or an octahedron. They live inside each other, and are conjugate solids, a by the names the mathematicians have given. And we're interested in both counting the number of arrangements, that is, counting how many different positions I can put an octahedron or a cube. The number is 24. That's the order of the symmetry group that goes with this figure of a cube or an octahedron. And then, on the other hand, the actual operations that take you from one position to another. And these fell into 5 classes. The loneliest class of all being the unit class. Mathematicians sometimes call that the trivial class. They always use the word trivial to describe something as though it was to be dismissed and not thought about it, but of course this is the most important class of all because it's the one we spectrally resolve. But the other class, the largest class, is 8 elements that are 120-degree rotations, followed by, in a group we call the T group, tetrahedral group, 3 180-degree rotations around the X, Y, and Z axes of SF6 molecule, if you want to think of it in terms of an actual chemical. And then the other half of the group, this is 12 elements, there's another 12 that consist of the 90-degree rotations around the Cartesian axes. X, Y, Z comes out of the board here. And finally, 180-degree rotations around diagonals of the various figures, octahedron or cube. The edges, basically, the axes that go through the edges are 180-degree rotations. And there's 6 of those that we're using the letter I to describe instead of the Greek letter rho that we used in the D3 group. And then there's this slide rule, and we're going to use that again. We're going to show that the cosets of the octahedral group are displayed on features. It's actually sitting there telling you, hey, here I am, I coset. So this, besides being a nice tool for doing multiplications, is also a nice tool for organizing classes, cosets, and other things that are of interest, particularly projective things that we'll get to later. Now, I'll skip for now reviewing those fellows there. That can come later on. In fact, I hope we have some time in lecture 21 to go into higher groups. But here is a set diagram showing all of the symmetries that we would call octahedral, tetrahedral, or cubic. And we're just kind of going to be focusing mostly today on the O symmetry. But I'm going to show just in a few minutes here some of the correlation tables that go with the other ones. So this is a group of order 48. We're mostly doing our work here with just the 24 elements that are shown on the cube previously. There's only 24 positions being shown there, and there's only 24 of the little operations being shown there. And that's how that slide rule works. Well, it works just as well for all 48. There's all 48 of them sitting there. And we have the model of the cube that we can access at any time. But this picture is good enough to do some things pretty easily. Obviously, it's much better to have one of these. Send in a box top and $10 and I'll get you one. But you can also make it yourself using stuff that's on the web. Anyway, we went through the character tables of the octahedral group, which consisted of a singlet A1, a singlet A2, a doublet E, and then 2 kinds of triplets. Basically, the vector and the tensor, we'll see later on how that is determined. And then we made a correlation between the representations of the octahedron if they were just asked to look at the group D4, which is a subgroup that has none of the 120-degree rotations and only a select number of the rotations of 180, either on the XYZ axis or the edges, or 90-degree rotations, you see. And that's a group D4 whose character table is sitting, let's see, somewhere here on this thing. I think I have the character table for D4. Yes, here it is. With the elements crossed out for going to a C4, and that's where we really want to go. Today we're just going to sort of jump from this big group here to this little C4, because the correlation table for the octahedron 2C4 has nothing but zeros and ones, and that's good. I don't like getting a 2 anywhere, because that leads to an ambiguity that you have to solve some other way. So with a correlation table like that, we're going to build all of our stuff today just looking at this structure right there of the octahedral representations going out, splitting in 3 for these two triplets, but only the particular 3. And then the doublet here splits here into 0 mod 4 and 2 mod 4. And then A2 is just 2 mod 4 and A1 is just 0, 4. So we don't have to do any more work on those. It's these guys here with their degeneracies that we need to focus most of our labor in order to make this into a theory that really works for us. So I pointed out that when we split a projector into, say, 3 parts, or split it into 2 parts, a doublet and a singlet, such as is going on right here and here for these triplets, we better understand it, I think, if we just draw the level diagrams from going from octahedral symmetry, stopping along the way just for a moment at D4 symmetry, but then continuing to C4, for which there is no degeneracy in the C4 character table. So we will see all singlets, but we will see them according to that labeling of number modulo 4. So this is a sort of a nice map of what's going to happen as we take the idempotents from the center of this group, the ones that commute with everything, those projection operators PT2 and PT1, as well as PE, and split them, this one in 2, this one in 3 parts. So we're going to go directly to this splitting today. Okay, this is another picture from the Principles of Symmetry, Dynamics, and Spectroscopy. It's the level splitting that we were just talking about. That's directly from that figure in that textbook. It lacks color, it's a black and white book. So
sorry, if you want to make an example for each of these A1, A2E, T1, and T2.
Right, that's the
standing
octahedral
wave. No, I mean the A1, A2, which was the reflection A2, I think. Am I right?
Say that question again.
I mean, if we want to make an example for each of these
yes.
in the real world.
In the real world.
Yeah, A1. What is A1?
Okay.
Is it the moving waves A1?
It's about as standing as they
standing
get.
waves.
Yeah, and in fact, if you're going to do the thing that we did when we just started talking about the orbitals with respect to D3, we split it into angular momentum multiplets, the atomic S,
yeah.
the angular momentum 0, okay, remember that, then the atomic P, angular momentum 1, triplet, right? Okay, and then the next stop was angular momentum 2, the D orbitals, the things that make all of your center of periodic chart, the stuff this building is just totally working with.
Are DTs D?
Well, this one is S.
S.
Okay.
E is P.
This one is S with a minus parity. That's one way to say it, but it's not quite right. Okay, it's also a scalar like this one, but I would call this a pseudo-scalar. In 90-degree rotations, give it a minus sign. And the way you can tell that is look at the character table for A2. And the second half of the group, which is these 12 elements, all give minus eigenvalues for that one.
Yeah.
Now, who's the E? Well, E and T2 go together to make the 5D levels of an atom. Now, we're going to go through this later, but you might, since you asked the question, this is a D, and that's also a D, the other half of it. Okay? Now this one, this triplet, that's the P. Okay? Does that make sense?
Yeah.
Okay? And then when you go to the F, then you're going to use this guy. You got to make 7 things, right? You're going to go with this guy, and this guy.
All right.
You see? Now it's getting complicated. All right? But that's a really good question in the sense that that's kind of the way most people learn their group theory, because they already know about sp, df, g orbitals, and so you can use those to sort yourself out with these. The problem is when the angular momentum gets high, like 20 or 30 or 88, which is on the wall back there, well, the group theory really comes to rescue. So that's an important idea. Yes, okay.
The index of D4 in O is 3, right?
Well, the D4 has 8 elements,
Yeah.
and O has 24. So the ratio of those two numbers, just called the index, is indeed 3. 3 times 8 is 24.
Is 3. Now, if we look at the correlation table there, it says for the A1 representation of D4 that there's going to be one A1 representation
Yes.
of O and one E representation of O. And now the sum of the dimension for the representation E and the sum of the dimension for A is
Mhm.
equal to 3.
Yes,
Yeah.
yes, absolutely. And in fact, that makes it a full 3-dimensional vector.
Yeah.
That was one of the splittings that you saw here.
Now, what I wanted to comment about is that for a lot of subgroup splittings and correlation tables, the relation between that dimensionality and the index of the subgroup in the group will hold.
Well, we're going to see that in spades here, because we're going to be taking the C4 group, which is 4 elements, and it appears 6 times as an index of 6 in our group. That's what we're going to work with today.
Yeah. Let's
Okay? So when we go O to C4,
go to C4.
right, that's all we're going to do today.
Mm-hmm.
Okay, we're going to play this thing. I just want you to see some of the other ones before we get there, because we can call on them to help us
Yeah.
see some
Now
things.
I'm seeing it on the C4 table.
Yeah.
But I haven't necessarily gone through the details to see
Well,
if they were
yeah,
guys
it really helps
expected
to do that. We'll later on see examples of cosets of three cosets.
Yeah.
Today it's 6.
Then there's 6 cosets.
Okay. The
Well-
index tells you how many cosets you're going to have
Right.
in your.
As well as conjugate subgroups. Cosets and
Well,
conjugate subgroups.
we'll talk about the conjugate in just a minute here. The conjugate or self-conjugate subgroups, and that brings up this 2 here. This is what I call a normal, I don't call this, I would say this was abnormal, but the name of the group D2 that consists of Rx, Ry, and Rz squared, that's 180-degree rotations around X, Y, Z. That's our favorite 4 group. But there's another one in there. In fact, there's another couple of ones in there. Whoops, let me go back here in just a minute. But anyway, what I'm doing here is I'm showing the D2 coming out at the end instead of the C4. Okay? It's A1s and B1s and B2s and A2s. They all show up here, and they have their own meaning. That's the trouble with this notation, is you can't just glue this A1 to this well, you can, in fact, almost always get the A1 of a subgroup to be the A1 of a big group, however big, including O. But the rest of them can really make your life miserable if you don't know what's going on. So you have to be really careful. And that's why these correlation tables are really good things to make and hold on to. And they guide you through things. Now, a normal subgroup is a group which can be transformed only to itself. It's normal in the sense that it's sitting there using the normal coordinates which the octahedron has. The normal subgroup is a rotation around this axis, 180, another element this way, and another one element this way, and there's the identity. That's the 4 group. Okay? No transformation in this group will change that group. But if you start using the 180s around the diagonals, look out. And that's what I want to show. Normal versus unnormal D2. Okay? Unnormal D2's got the same R3 squared that this one does, but it's got I3 and I4 instead of the other Cartesians. This is an unnormal subgroup, but it's exactly what we want. I don't like normal, I like unnormal. Because it does not have this 2 here. Its correlation table is kind of weird because the B1 and the A2 and all kinds of play funny games with each other. There's a switcheroo, you see, between the correlation table for the normal D2 and the unnormal D2. You've got to watch that. That has tripped some people up. You got to be careful with that. These two flip positions. Okay, we'll get into this maybe later on, but this degeneracy ambiguity, that's poison to what we're doing today. So we like to use the D2 that comes out of D4, and then we don't get in trouble. We don't have a degeneracy ambiguity.
Sorry.
So that's an important.
There are there 6 eyes? Do we
there
have
are
6
6 of those 180-degree rotations.
Which one do you choose for that D2?
Yeah. Remember, there are 12 lines on this, that is 12 vertices of an octahedron, edges, right? That's an edge, right? That line that I'm tracing. And the angle perpendicular, the rotation perpendicular to that.
Those eyes are the rotations that are on the equator? So they sort of mimic the X and the Y and the other D2.
And there are 3 equators. There's 2 of them in each equator. This equator around there, then there's an equator around there, and then there's an equator right there. And each of them has 2. Each of those 3 equators has 2 orthogonal.
The one perpendicular to the R3.
Yes.
Yeah, am I right?
Yes.
Yes.
Absolutely.
That's
if we
right.
had the codex.
And we'll show lots of pictures of this because that's the way we're going to make our cosets today, okay, is out of those things. We're going to use them as labels, in fact, for some quantum transitions, if you will. Now, as it gets more complicated as we go out to OH, I'm going to use this correlation table today. Now, this one right here is neat because it knows the parity of everything. Is it even Garada or is it odd? And I see a typo here. That should be a U, like all the rest of them. Listen, the odd ones, okay? And we're going to be playing with this particular induced representation, A1, E, and T1, but T1 is going to be odd. A1 and E1, A1 and E are both going to be Garade. That's even, and that's a cool thing that we're going to see today as we're passing by the induced representation and its spectra. Okay, and also the C2V correlation tables also have this ambiguity. If you use the Cartesian one, if you use the one that's unnormal, it doesn't give you any headaches. So I just wanted to point that out as a little bit. Okay, let's get started here. This is the thing we're setting to do today. We're going to use C4 characters to split the idempotence of this giant, the octahedron, 24 element rotation group for a Cuban octahedron. Okay? So what we're doing is we're using the correlation table here that tells us A1 doesn't split, it's just the A1 of C4, which I call 0,4. Other people would call it an A1 or a little A1 or something like that. A2, well, it goes to 2 modulo 4, representation of C4. We're going to be interested in this one, and this one, because we're going to have a local symmetry, 0,4. We're going to be fooling around with just this projection operator right here. I'm not going to worry about this one today. And then I'm going to worry about the ones that do split. These two I don't have to do any more work on. They don't split, they're irreducible as they are. But these are reducible, the ones in the center, the ones that commute. We have to split them. This one in 2, this one in 3 pieces, and well, if we were working with this one today, we'd also want to split it as well. We'll show pictures of it being split, actually, in passing. Okay, so that's why we're doing this, because we're going to use the projection operators of this subgroup whose completeness relation, that is 1 equals the sum of those projection operators for 0 mod 4, 1 mod 4, 2 mod 4, and minus 1 mod 4, which is 3 mod 4, okay? We're going to be using this completeness relation and applying it to each one. I don't need to do those two, but I have to apply it to each one of these things can split. And what are they going to split into? Exactly what this correlation table says they're going to split into. 0 mod 4 and 2 mod 4 is what we're going to split this one in. So I don't need to look for this one doing anything, and I don't need to look for this one doing anything. I just need to concentrate for E on those two. And then for T1, same thing, except I don't have to pay any attention to that one. It's only this, this, and this, that you see in the correlation table, are going to give me a non-zero product, or non-zero splitting product. And T2, if I were doing that today, I would pay no attention to 0, 4, and I would look at those 3. Okay? So this is just to make a connection between, you see, this is guiding you into what the algebra is that you're going to have to do. So a good portion of the first part of this lecture is just going to be doing this algebra. Okay? So that's the idea. We're going to split using C4 projectors applied to O-class projections that need splitting. Again, these two don't need splitting. They're already irreducible. But these do. And we have two different notations running here. One of them is in principal symmetry dynamics and spectroscopy, the Wiley group, which has sometimes 2 subscripts, superscripts, subscripts. That's what I got used to. But now, in order to build our little slide rule and keep our algebra simple, I'm only allowing 1 symbol and 1 subscript, and maybe a hat. That's the inverse, that's the squared, which is the inverse of these. The little tilde means inverse. And then this thing here, that's awful, so I'm just calling it X, Y, and Z, rho. So I'm going to use rho, letter rho, for the 180-degree rotations there. And then this one in particular, R cubed, I don't want the cube there. I'm just going to put a tilde on X, Y, and Z, 1, 2, and 3, and same here. Okay? And then I'm not going to change the I's. Okay? They're fine. All right, so in the newer International Journal of Molecular Science, where we start doing this stuff, making group elements correspond to parameters of quantum transformations or transitions, we are using this lower notation, and most of the time we'll use that up here. Okay, so here's the character table for C4. Well, that means that those are the projectors right there. Now it's a little out of order. I got 1 plus, this is the rho Z, this is the RZ, a rotation around Z by 90 degrees. Rho Z is that thing squared, so rho Z is r squared for z-axis, and then it would be the same for y-axis and x-axis too. But this is totally a subgroup that's keyed to the z-axis. So here's a scalar one. Here's the one with an I, a minus, and a minus I. Then there's a pseudo-scalar here that's plus, minus, plus, minus. And then there's the conjugate of this right there. Okay, so these characters you see are giving this representation. Okay, and the other notation that I'm going to be using is this thing. This is the actual standard notation for a representation is a D. This is a little d to represent it as part of a little group. And the m number, that's momentum. Here's the actual element that's in question. How many p's do you have? 0, 1, 2, 3. 0, 1, 2, 3, you see. That's the p. So it's momentum times the number of translations around a square, which can be 0, 1, 2, and 3. And the momentum can be 0, 1, 2, and 3. Those are the numbers right there, modulo 4, that correspond to quantum momentum of this particular group. Okay, so the development that we're doing today is to get irreducible projectors. And it's the diagonal ones, the ones that are idempotent, that we're going to be worried about today. So we're going to take those idempotents, those little idempotents that are going to run into this great big idempotent that is the thing that we worked out last time with these guys right here, are the projectors that commute with everything in the octahedral group. They're the all-commuting central projectors. Along with these guys, they also do that, but they're already done, so we're not talking about them most of the time. Okay? So we're going to be building T1004, for example, or T11414, you see, just by multiplying it by a projector. Now remember, they commute with everything, these guys. So they commute with these. You can put them on either side. That's very helpful to know, because next time we're going to do off diagonal, and we need to know that, do that. And we're going to use left coset combinations, because after all, we're going to be multiplying this thing by elements that sit in the sum. That's whole class sums, you see. It's quite a job that we've got for here, all 24 elements divided up into 6 cosets, you see. Cosets made by taking the C4 group, which is that, multiplying it by first the identity, which does nothing, but then multiplying it by row X. Then the next coset is going to be multiplied by R1, makes that. R2 makes that. We need a picture of those. That's something
quick
we
question
need.
here.
Pardon?
Which C4 did you choose?
We chose the Z-axis. Isn't that traditional?
The Z-axis.
There it is.
But you could choose any C4 group.
You bet. It's not a normal subgroup.
Right.
There's 3 of them,
Yeah.
corresponding to the 3 axes.
It's
Okay.
different for tetrahedral.
Yeah. And the tetrahedron is isomorphic to this group, so after we get done, we can walk over the TD. Just change the notation a little bit.
Yeah, but there's a tetrahedron, not a TD, but just a regular tetrahedron.
Oh, T is weird. It's half of O.
It's half.
Remember?
Yeah, and that's
Okay,
normal.
so we're essentially taking care of it.
Yeah.
We already have done the characters for that one, remember? That was a weird one that had 1 triplet and then 2 complex pairs to make its way in the world. Okay, so we're doing this, and that means is we're going to be doing this. So here's C4. There are the elements of C4. Unit, rotation by 90 degrees, rotation by 180 degrees, and rotation by 270 or minus 90. So there's a subgroup sitting there, right there. Okay? Okay, next coset. Okay? Say I take row X as my next coset. It's on the back side of this thing. Okay? It's on the back side. Here's the, I've got to find my Z-axis here. here's my little guy, right? There's the 1. Now forget the sigmas. This one has a full OH in it. This one I've left them blank. Okay, but you see 1 RZ, rho Z, and RZ tilde, which is the inverse of RZ. Okay, flip it over, and that's what you've got. This thing right here. Okay, the Y is over here because I flipped it, right? But there is the other second coset. Okay. I've got I3, I4, X, and Y. Okay? That's the back side of this. Okay? Then, R1. Okay? Now, R1 is an operation that comes out of this corner. You can see a little R1 a line sticking out. Okay, that's the actual operation axis. Okay? It's going to take this thing and throw it around to this side. Takes the 1 and puts it to R1. And that's this whole coset right here. Okay? So now we got 3 cosets. The rest of them are the same idea. There's this guy right here. That's the R2. Little R2 sticks out down here. Okay, sort of opposite, pointing across R1. Okay? It would take this thing and throw it down to this side. There's the R2, right? Okay? R2's got an I2, and it's got an R3, and it's got this guy, RY tilde. Now it's using a 90-degree rotation. Okay? Now any one of the elements in these cosets could be used as a label for that coset. But when you have things like this, you know, there's sort of a democracy. I don't get in trouble. Okay? Well, here's the top and the bottom. That's the y-axis. Okay? You see the little r1s, 120s, 1 and 3, there and there. And then the I6 and the R tilde X. Okay? When you do an X rotation with this thing, you see, you turn it up. You turn this face up there, and that's the X-axis right there. Okay, and there's the Z-axis as well. Okay? So, this gives you a picture that I have not found in any other textbook, including mathematical ones. They get tied up with a Cayley graph, okay? Well, a Cayley graph is good for something, but not good for this. Okay. All right, now the hell breaks loose. This is the worst part of the lecture video. I want to show you the development. I'm going to just, you just have to sit there and watch this, but imagine you had to do it. What I've got to do is I'm actually going to sit here and multiply, you see, this projection operator, which is sum of 4 things, times each one of the 24 group operators. That's what the projection operator formula asks us to talk about, okay? So we're going to take, and in the process we're going to get these numbers, you see. These are the irreducible representations of this octahedral group. Well, they're irreducible representations star. We've got to be real careful about that, especially today, because we're dealing with complex numbers here. If you're not, then you forget that star, but I tell people always remember, because that's a real way to screw yourself up when it comes time to do a representation that has complex D's. Okay, so each time I take another group element, I'm going to have a different character from the character table of the octahedrons. These are the octahedral characters right here for each of the classes that it has of rotations, which we went through before. Okay, so I'm going to be multiplying here by projection operators, you see, and the projection operator that we're talking about is this one right here, that's made up of the coefficients that are these little d's, these C4 characters, these little d's here, which are just plus and minus 1 and plus and minus I, you see. So these will be numbered later on, but right now I'm keeping them out in the open so you can see the structure of how we're putting the sum and multiplications together, okay? And after we get done doing the unit, okay, there'll be another C4 times a operator, and then another one, you see, there's going to be 24 of these things, you see, in order to pull this off. So it's really important to see the structure because we're going to make it a lot easier to do. Okay, so there we go. All I did here was take the order of the group. You see LMU order of the group and put in 24, and then I haven't specified the representation yet. This is supposed to be general, so the mu here that goes with the dimension factor is going to be put in at the end. Okay, when we finally get a formula that doesn't take up 6 black whiteboards. Okay, so we're basically just going ahead here and adding, expanding these things a little bit each time. Here's the order of the group, just like it was there. But I just wanted to show you that one start with because we're going to make a whole bunch of these. Okay, now this is the next little piece to the projection operator from C4. Okay, the rho z, and then there's the RZ tilde. Let's just go ahead and watch this thing taken apart here. Not much being done there, but you see the rho z, everything's the same so far here. And let's see if there's anything I've got to. Oh, I'm going to reorder each one of these so that the same elements come up. You see, when you do a coset with rho z, it puts a rho z in the first spot because there's the entity, and then it puts a 1 there because rho z squared is equal to 1, and then when rho z hits a 90 degree, turns into 270, when it's at 270 turns into 90. I want to keep the same ordering of those, so I'm just going to turn them around, and you see that means I'm going to permute these little sub-indices that indicate what group element I'm talking about in C4. Only have to do this for C4. Okay, so there is what I'm after. This is now with a 90-degree rotation. Okay, so when I multiply the 90-degree rotation by 1, I get this thing. Then I multiply it by rho z, I get 270. Multiply it by this one right here, I get 180. And then multiply it by the inverse of RZ, I get 1. So I got to turn that one around, okay, to make it look like this. That means I have to move the coefficient accordingly. Okay, that's what we've got to do. Everywhere, every time we have an element, we've got to do that. You see, we have to go through this 4 steps for every element. We started here with a unit, okay, but in the next round, we're going to have a row X. That's our first coset. Remember, X, Y, I3, I4. Okay? So we're going to put that together now. Reorder. Okay? Back to the front. Okay, well, different elements show up, you see, there. But I've got these things permuted correctly. Now let's get rid of the tables and just carry this one out, you see. That's what we need. We need this for every, now R1's next, as I say, etc., another 22 times. So this is, there's a lot of arithmetic in this. If you do it this every time, I mean, then you'd be right to take Schrodinger's advice. This is a group and pest. This is a mess. Okay, well, it's not a mess because I'm being orderly, but it's very voluminous and labor intensive. So it's this sum right here that takes care of all 24. And what I'm doing is I'm lining up the cosets this way instead of vertically, lining them up horizontally, okay? And then each of the 24 columns, starting with this one right here, just follow this line up. This guy, this guy, this guy, this guy, that's a column, okay? Each one of those numbers, it's got to be summed up, and that is going to be the coefficient of the unit operator. Then the next one, rho z, remember, okay? It's consisting of a sum of this number, this number, this number, this number, well, times the character of the particular element in question, okay? And then so forth. All these question marks have to be filled up. And then when we have that, we'll have a projection operator in terms of cosets, and that's the neat factoring that happens in this business. So what we're going to be getting from each of these sums, each of the 24 columns is a sum of 4 products, a O character and a C4 character, and then appropriate dimension over order of group, and a normalization factor from each of those. This is going to give us the coefficient of the group element G of the projection operator, and that coefficient is an irreducible representation except for this L mu over the order of the group. That's the order of the day. And we did this for C3V and D3. Didn't feel necessary to go into so much rigmarole about the bookkeeping because there's only 6 things. We need to respect the rigmarole at this point. This is a big enough group that it's very easy to just pull your hair out and become bald. Okay? So, the P sum will be in the order of the cosets when we're done here, but we can also rewrite that in terms of actual group operators, and we will do that. So let's see a couple of examples here. Okay? This is talking about here the E. And as I said, we're only interested today in the local symmetry 0,4 of C4. So we're going to be focusing on that. But I'm going to go ahead and make a few of the others for later on. All right? So here is a set of numbers that I'm talking about. Okay? And this one's particularly easy because all of those numbers are 1s. The coefficients of the C4 operators are all 1, 1, 1, 1. Next one's going to have an I and a minus I. We'll do that one too. It has a 1, minus 1, 1, minus 1. But those are the numbers that are going to go in here. So they're numbers that we easily can put in there. Then it's just a matter of loading in each one of these with the correct character from this guy. So 2, minus 1, 2, 0, 0 are going to show up on these in various places from the chi-E. That's the octahedral character. Okay? So there they are. There's the 2 from the character associated with row X. It's this guy right there. Okay? I4 and I3. Well, they're all under the I class, so there's 0. Okay? And so forth. Okay? So what we have to do is simply product and add. This one comes 4, 4, 4, 4, 4, 4, and then minus 2, minus 2, minus 2, minus. This is very repetitive. Something's going on here that makes this job easier. We'll talk about that a little bit later. That's the actual factoring of these things. So here is the coset factored sum, and that's what we really want. These are the things that are going to be our wave functions today to diagonalize some weird tunneling thing. It's those 6 numbers. We only need a number for each coset. That's really what the factoring boils down to. For each coset. Okay? But you can do it in a broken class ordered sum. Now this is getting a little ahead of what we're going to talk about today, but when we get done and have all of these projection operators that are diagonal, we can also have the same number of broken classes. How many of those are there? That's the rank. Remember, the rank is the sum of the dimensions of these things. It's 10 for this group. So we're going to have 10 broken classes instead of 5 whole classes. And that's where you get the the idea. Remember, all of these R's are going to be parameters for some kind of tunneling process. So we're going to have 10 with the requirements that we put on it. We stay diagonal and we look at the this particular 0, 4 local symmetry. That's called local symmetry condition. We're going to be writing eigen values down using characters. That's what we're really doing here. I don't think anybody's done this, at least not this way that I can find. Okay? So we took care of P004. Let's look at 2,4 just real quick here. That's this guy right here. I use sort of a sick red color, which comes out brown on this screen, for the pseudoscalar. We're looking at this C4 pseudoscalar right now. The second component, you might say, of the E.
Question.
Yes.
How does each of these projectors transform under group operations in the
Okay, that's something we've discussed before. It's really very simple. Probably the best thing to write down about that is that these D matrices and the things that determine the transformation, okay, of a group element, okay, and we're talking about some coefficients of this thing. Let's just say J and K, okay. That's going to be the coefficient of the projection operator P mu J J operating on G P mu K. So if I put this together, I get a projection operator P J K. So that's probably the simplest way to say what is the transformation property of this. Another way to say it, which I hesitate to use right now, is the state projected by those, and then I just say JK equals this. Another way to write it is G operating on P mu J K gives you a linear combination of P mu J prime K, and then the coefficients of that linear transformation consists of mu and then J prime right here, and that's being summed over that J prime.
That's kind of more what I was wondering about, but what about G P G inverse? What about a similarity transformation on the projector?
Well, you just do this again,
Yeah.
right?
But you don't get, well, correct me if I'm wrong, but it seems like then you would not get back to G P G inverse equals to P.
No, you get it. Basically, that would be an outer product. You get a combination a factor of G's. The D's are transformed of individual state vectors. You make an operator. Each operator has two sides, so you're going to have two D's.
So these projectors that you're making are not invariant on your similarity transformations by the subgroup.
No. I mean, they're variant. That's what their job is. Their job is not to be invariant. That was the guys in the center. These guys.
Yeah.
Those guys are invariant. I attach this thing to it. Now I'm off into the real world.
Yeah.
Okay? And I can attach it to either side because this thing commutes with everything. Those are invariant.
Yeah.
These are anything but. This is where the physics is. These are things that describe the symmetric state being unsymmetric.
Yeah. I'll agree. I agree with that.
That's what it's real. This is really all about.
But sometimes you might be interested to describe this symmetric state as being symmetric.
Well, we've got one of those. It's called A1.
Yeah.
But that's the ground state, so to speak. of a system. Everything settles down. It looks the same in all of the symmetry directions. As I said, those two, A1 and A2, we already have done them. I don't need to go through this for them.
Yeah, but I'm thinking that there should be an E and maybe not, but I'm thinking that there should be an E and a T which are also symmetric around that forward direction, because we're working in the representation of C4, that is the isotropic representation.
Well, we're working off of that one column, 0, 4 of the correlation table.
Yeah.
Okay, I'm going to be just interested in, but right now I'm making this one.
Oh, now we're doing that.
Right?
Yeah, sure.
Same deal. And nothing's changed. It's just that we're not going to use that one today. I just wanted to, exhibit a few of them before we start actually using the 0, 4 ones. Now here's another 0, 4 one. This one involves T1. Okay, it's this guy that I'm looking at right now. So I've got this one, I've got this one. Now I just need this, and then we're off to the races. Well, this one is really simple. It's all zeros. Okay, except for the first two. Okay, so that's I think kind of neat. See if I've got anything to say about that. I think that's pretty well it. So here's the coset factored sum. There's the broken class ordered sum. A lot of zeros. All right. Now this one is going to also be of interest to us, just for the heck of it, and we're going to consider a wave function that uses that one. That's the moving wave component of T1. And you can see it's got i's in it. It's got plus I over 2, plus I over 2, minus I over 2, minus I over 2. So this is one where you really have to pay attention to keeping the star in place when you talk about well, I don't have a formula for the p's up there.
Sorry, can we go back to the last slide real quick?
This is the T1
Now this
A1.
one, yeah, this one actually does look invariant under the similarity transformation, because unless it would change the coset. So
These are the only two cosets involved. The rest of them are 0. But it does have this one.
Okay. So is the second coset there the one that's on the same axis?
Yes,
Yeah.
we'll see that.
Then-
Yeah, rho x, 180-degree rotation.
Right. So this one actually under similarity transformation is invariant because...
Well, don't call it similarity, because similarity always means T inverse. It's two transformations. It's this kind of transformation that.
Yeah, but I was
talking
thinking GP and G inverse, GP G inverse, because the G's will commute with the first coset there, and then it doesn't matter on the second coset because they're all the same value.
Well, it sort of does matter. None of these operators here are all commuting, that's for sure. The only one that's all commuting is 1.
Right, but I mean with the subgroup C4.
Oh, well, subgroup C4 respects what we're going to call local symmetry, and that is the z-axis, which consists of these two, really. The rest of them got killed because they weren't that, so that's one way to look at it.
Which makes it easier to have this, the axial symmetry there.
Yeah, and by the way, when things like that happen, there's always a reason for zeros. Remember when we showed how local symmetry and global symmetry meet each other? It's death, right? 0, that's what's going on right there.
All around the waist.
Yeah, we'll see that. Well, actually, pictures today. Okay, we did this one. We won't need that one, but there it is, just for the heck of it. It kind of looks like something we've already seen. There's a moving wave now, and it's got eyes, just slightly different plus and minus signs. And let's do a problem. Okay, as I said, today we're interested in a particular induced representation. We're also interested in studying what is an induced representation more clearly. So that's one of the main reasons that I picked this example, because it's the most, I think, lucid example of that. Anyway, what we're going to do is we're going to, as we usually do, consider a classical problem that involves a K matrix made up of various parameters corresponding to various little springs that live in there. The S here corresponds to the K spring. I don't make them equal because there's little angles here with the K that would make it be S cosine, or it'd be K cosine squared of the angle with this coordinate and this coordinate to make the 2, 5 component, okay, which would be right there, all right. But they're all pretty equal except for the ones in the, they're right on the diagonal, corresponding to flips between 1 and 2. This is 1 and 2 quantum state, okay. Some waves are going to be living in little valleys there. And then here it's a classical thing that involves just coordinates of motion. These things can only slide on these frictionless rods that form an octahedron by the arrangement of the equilibrium position of those springs. Over here we have a Hamiltonian. Some people call these Hubbard models, when you just make up parameters for tunneling from one place to another. And this particular one has nearest neighbor tunneling parameters S going, say, from the valley state number 1, not to 2, that's next nearest neighbor, okay, but from 1 to 3, 1 to 4, 1 to 5, and 1 to 6 would be these 4 numbers right there. It would be analogous to these 4 springs you see are connecting nearest neighbors, you see. So I'd be talking about this spring, and that spring in the top row for coordinate number 1. Here we're talking about a wave function number 1 feeling through evanescence the wave function of not 2, it's too far away, but that would mean that this t and this t and this t 0 for most of the models that would make any sense in this particular problem. And I would have, though, a non-zero but small tunneling from 1 to 3, from 1 to 3, or 4, or 5, or 6, you see, but not 2. Okay, that would be that model, pretty much. Well, really very simple physics, but it's octahedral, so it's right down our alley here. Now, what does this symboling mean here? Let's look at that. You get it from the correlation table, but let's just go ahead and build it. We're going to assume, you see, that every one of the local valleys, but in particular the first one, satisfies that. It's invariant to a 90-degree rotation, a 180-degree rotation, and a 270-degree rotation. Power P equal to 0, 1, 2, and 3 of the Z operator, R3. The rotation, and now 3 refers to Z axis. Okay? Don't confuse that 3 with this particular state that happens to be sitting over here on the x-axis. All right, is that clear? Okay? So this is a local symmetry condition. No matter what I do, this is kind of square here, but it doesn't matter because I'm going to do 90-degree rotations of whatever's in there, and it's going to look the same. That's what we mean by C4, 0, 4, 0, 4 local symmetry. It's the easiest one. Okay? Now, the projection operators is some of those things. So the idea is that a projection operator 0, 4 on that state is not going to change it. If this is true, then this is true. Remember that 1/4 there is going to add up to one of them. Okay? And that this applies to all 6 of these base states. These 6 base states also have their local symmetry relation. This is just the local symmetry that's the same as the global symmetry. Okay, so what we're going to do is, and here are all the cosets, here's another way to look at what all of those states are. Okay? I start out with this state right here that satisfies the fact that I can do a projection operator with all 3 of those things and it won't change it. So this is a local symmetry of this particular guy right there. Okay? Now I do an operation, say I do an R1 squared, that's a rotation around the number 1 axis by 180 degrees, a flip. I'm going to flip all of those guys. Well, that line right there is associated with this coset. That's Rx squared. The x-axis being right here. I just flipped this thing completely over to there. So this is turned into that, which is that. Now, we've seen these cosets already. Not quite in that order. We switched to columns 1 and 2 because I wanted to keep the 1r squared, which we call rho z, in a little subgroup, as a little subgroup of the foregroup for later use. So, except for that, this is the same as that, with this notational change here, okay, where rho x becomes r1 squared, rho y becomes r2 squared, rho z becomes r3 squared. Those are those numbers right there, those things. Here's the modern notation. Okay, and you could see that the this particular one has flipped. There's Rx right there. That's in the right position. But the I4 and the rho y, which is R2 squared, have changed positions. And then I3 is where it is. And that's the way it is all the way through this. So that's a little confusing. That's why I keep this 2 forms of notation, old and new, up front. Okay? Now when you're studying, going through and studying this, the page numbers to go back and look at these things as you go through this thing. Okay, now what is an induced representation? Finally, we're close to the end of the lecture here today. We're within 15 minutes or so, and the battery's looking good, so I think we'll make it. Memory may not be so good, but we'll see. I just wanted to show you a particular operation, 180-degree rotation, that involves one of these I's. I'm particularly interested in I4 for a moment. I4 goes through perpendicular to the z-axis. Okay? If this is the 3-axis. Okay, z-axis. Okay, this thing is perpendicular to that. Okay? And as a result, you imagine twirling that little thing 180, we're going to take this state, like we said, over to that one. That's the flip. All right? What does I4 do to all the other states? Okay, I4, well, I4 is in the same coset. This is the way you do the arithmetic, old-fashioned way. It's in the same coset as R1 squared. So I can immediately replace that with R1 squared. Okay? And R1 squared is what we call state 2. Right? Okay, what does I4 do to state 2? Okay? Well, state 2 is defined as, I'm going to use this guy right here, R1 squared. So I got to do an I4 times R1 squared. Now we should get out our little cube and we can do this multiplication real quickly. But I'll just tell you right now, it's RZ cubed. Okay? Where is RZ cubed in this set of operators here? Okay? RZ cubed. It's got to be here somewhere. It's number 3, so oh, it's right there. Ooh. We come home, right? Back to 1. Okay? Now, do it again. I4 times the R1 that's labeling this guy right here. Okay? I4 times R1, we get our slide rule. It turns out to be I5. Where do we find an I5? Oh, no I5 there, no I5 there, no I5. Oh, right at the very end there, I5. So this thing right here is the same as R2 squared. Okay? Or anything else in that coset. Okay? That's number 6. And let's see if that's right. I5, yeah. It corresponds to number 6. Let's see if I've got that right. Yeah, 6th one. Okay? And I4 times R2, that gives me an I6. Where is that? It's in the 5th one. I4 times R1 squared, it gives me an I2. Where's an I2? I see one right there. It's in the 4th one. And finally, I4 times this R2 squared gives me an I1. That's number 3. Okay? So there's your induced representation of this particular element, I4. One of 24 elements in this octahedral group. This is how you take a little representation, 0, 4, and up arrow it, induce it to the entire group. This is now a 6 by 6 representation of the entire group. This particular one is just representing I4, but we can represent them all. Okay, so that's what the notation is. Now I3, look at this one, I go through and work that one. I don't need to go through this, I can just look, you see. I can sit here and figure out where all of these go really easily, just from this diagram alone. I don't have to go through the multiplication, I just am doing it. That's another way to get this one, get these induced representations. But you can also do it to a linear combination of the i's, say. I could do the whole darn group, but let's just do the i's, okay? So I got little number here, I1, arbitrary, I2, arbitrary coefficients. I make a big fat element, I, and then I do a representation of it. And I just write down the coefficients in the positions that it belongs to. This is more of this labeling by group operator. It's a little bit of a switch from what we've been doing, but take it for what it's worth. And then, you know, I3, okay, with this one here, that's just an I3 there, an I3 there, okay? Then over on this side, I've got an I3 here and an I3 there. And then conjugate to that, there's an I3 and an I3. So all of these matrices, as we've gone since they're 180-degree rotations and unitary, they have to be symmetric. All right. Now let's do some projection of this representation. First of all, scalar eigenkit. We know what the answer for that was. All ones. So I'm going to be getting a symmetric representation, a wave function that is equal amplitudes and phase everywhere on the various valleys of that quantum pseudo-potential or whatever it is. And then I'm going to have a vibration that just consists of breathing for the classical model of a molecular vibration. Here's where it starts to get kind of neat. I can then produce for you a state, an eigenstate of the tunneling matrix labeled by E, and for the things just using that PE that we wrote down before. Consists of 1, 1, minus a half, minus a half, minus a half, minus a half. Okay? This goes with this coset, this with this. This is 1, 2, 3, 4, 5, 6 coset. Okay? 1 and 2 are opposite ends of the octahedron, you see. So I'm going to have here a number 1 and a number 1 right there. Or if I don't like writing 1/2, I can put a 2 here, and then all the rest of them are minus, 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 minus 1. Okay? So it's 2 to 1. This thing right here has 4 times the probability of any of these states that are on the equator of the z-axis. Remember, this is state 1, this is state 2, this is state 3, 4, 5, and 6. Okay? And they all have the same number, reduced in probability by amplitude by 2, and probability by 4 squared. Okay? This is the same deal here. Now, this is a little bit, but this thing should really be twice as long as these guys, and these guys point inward, those guys point outward if we're considering radial motion to be positive and inward motion to be negative. So there's a mechanical model. There's this wave function. This is a weird one. This we think we understand because we think we understand classical mechanics. Now here's another projector derived in the next lectures. The off diagonal. It's 04 on local symmetry, but global symmetry is something else, and it has a 2-4. So here it is. This is what it looks like, right there. Doesn't have anything here because local and global are conflicting. So it only gets up with numbers on there, and that's what you see. Alternating, plus, minus, plus, minus, plus 1, minus 1, minus 1, as I go from. This would be 3 to 4, 3 to 4, both the same sign, and then 5 and 6, 5 and 6 are minuses. So we'll be getting that guy, this guy, later on, next time. Okay, but that's the coset sum that we're going to see coming out for the T1 now. Okay, so what is it showing? Well, remember, it's all zeros. So every one of these things out here on this girdle, unlike this thing, are 0. Okay, so there's nothing but zeros. And then there's not a 2 and 2 here, or 1 and 1 here, 1 and minus 1 here. So we're going to see a plus 1 on the 1, and then 2, number 2 state, it's got a minus. Minus. Okay? That's a T1 standing wave.
Quick question about these E functions here.
The E.
Yeah. It looks.
This guy.
Yeah, it looks like the column vector that you have there.
This guy.
Does have the C4 symmetry, if I'm reading it correctly, but then the pictures don't have the C4 symmetry.
Oh, well, these guys destroy that symmetry. Okay.
How so? So is one of those pictures?
Oh
the
no,
column vector?
this one has both local and global symmetry 0, 4.
Yeah.
Both indices are 0, 4 here.
Yeah. Right.
Okay? So it should be locally, and it just by the fact that it goes radially, it is.
Yeah.
But then if you look at the whole thing, you see that if I turn it 90 degrees, that these guys are going to go into each other.
Yeah, I'm slightly confused about
Not like those. Those
how
guys.
how does the vector relate to the picture there?
How does the vector relate to the picture?
Yeah.
Oh, 1, a vector 2 should be coming out of here.
Oh, okay.
Just like this is plus 2.
Oh, okay.
Okay?
Okay.
Then this guy's also plus 2.
Okay.
Plus, right? Then all the others, 3 is minus, 4 is minus, 5 is minus,
Okay, now
6, you got it? Right,
Yeah,
don't
I was a
confuse
little
1, 2, 3, 4, 5, 6 with the axes 1, 2, and 3.
Confused,
Does that make sense?
yeah. Yeah, I see.
Okay.
So that one does have C4 symmetry.
Yeah. And so does this. That's the T1.
But
This
then
was the E, right?
EG2 looks like it does not have C4 symmetry.
No, it doesn't. It is actually, let's go back here, it's 2, 4.
Okay.
It's a pseudoscalar locally.
Okay.
Globally, actually, that's the global position, right?
Okay.
This is local position. Okay? And this standing wave is accompanied by, and this is a hard drawing to do on Keynote, but these are the complex ones. This guy here that we wrote down, I guess I didn't bring up the thing that we calculated for this particular guy, but this is what it's going to look like. A +1, a plus I, 90 degrees out of phase, and then a -1 that's 180 degrees out of phase, and then a minus I that's 270, and then back home again. That's something that's got angular momentum. And this has got in the other direction. So these are the plus and minus 1, 4, or x plus I, y. Those are x and y standing waves, but now they've been phased and summed. So this is what makes this a non-trivial example, because these two components correspond to the x and y angular momentum states. Whereas this one is just a z angular momentum, and it's a standing wave. The 0, 4 is totally real. This is complex. So if you add and subtract these two, you can get some real waves, and that's what they look like. They're your p orbitals: pz, py, px, x, y, and z. P-like waves. That's what T1 is. You remember you asked about what T1 and A1 and things were. Well, here's T1 showing its true colors, its true blue color. Okay. And here, of course, it's just a vector translation of this whole thing. That's what it is. The three components of that. Okay. Now, here's the cool thing. That if you stick these vectors into this matrix, they give you eigenvalues plus 4s. Now, if s was negative, it would be down, but I'm assuming that that s is negative there. Then h, okay, this particular one, let's look at this one right here and this one right here, for example. Actually, I would prefer to look at that one for the e, but I'll show you a better way to get this. But this is predicting a 2-to-1 ratio of the shall we say, the transition frequencies. And in fact, they would be active. This is an opposite parity, and this is an opposite parity, so they go like bandit. And these are the answers to the eigenvalues for this. Now, those are actually already in our calculation that we just did of the projection operators, but I go ahead and show that. I also want to show the parity. If we'd done this using the full subgroup chain, A1G would show up if I had a local symmetry A prime of the full C4V, C2V local symmetry associated with using OH, the full 48 element group. And then I would get an induced representation consisting of A1G, EG, and nothing for T1G, but I do get something for T1U. And that's what we have. That's what we have in this particular induced representation. Full symmetry with parity. Labels it correctly. It's easy to do just with correlation tables. You don't have to sum over projectors or things. So, what I'd like to do is introduce you to the idea that these projection operators provide us with, and we're only talking about the I's now, remember, we can use those as our elements that determine the tunneling. I can go ahead here and read those eigenvalues out just from the numbers that sit there. The I16 operators are the ones that are nearest neighbor. They're operators that move us from 1 to 3, or 1 to 4, or 1 to 5, or 1 to 6. Those are the nearest neighbor operators. This guy, I3 or I4, they were the ones that turned the thing completely over, took 1 all the way over to 2, and 2 back to 1. That's a 2 neighbor jump. Normally we'd set these equal to 0 and set each one of the I1, 2, 5, and 6 local symmetry. They're all the same. Those parameters have to be the same to have the local symmetry. Otherwise they're going to mess up our eigenvectors. But here are the eigenvalues that you get. Plus 1, okay, for A1, I'm drawing it the way it is, 1 positive up, but it's turn it over, it's what we had just a minute ago. Minus a half for E and 0 for T1. That's nearest neighbor. What if you turn on double jump? You get plus 1 and plus 1. The E comes up and sits next to the A1, and the T drops to minus 1. That's minus 1. Okay? So these are just copied from what we did before with the splitting of the projectors. You see you get the eigenvalues for free, along with the eigenvectors. And that's the point we made about Fourier analysis. That the irreducible representations, that's those little e to the I, k, x's, they serve multiple jobs. Transformation coefficients, components of eigenvectors, components of eigenvalues. That's what group theory is so powerful. It does all those jobs at once. Pulls it all together. Now, if you want, this is a very untrustworthy slide, but you can go ahead and say, hey, what would happen if I were to go ahead and just do the operator, had all the i's equal and all the i's equal. Works pretty well. If I set one of them to 0 and the other one, and let the other one go, or vice versa. So take this this with a little grain of salt. We're going to talk some more about that sort of thing tomorrow. Now, we have just a few minutes here. I'm going to go ahead and show where the 0, 4 shows up. 0, 4 shows up as, for example, right here. This is an angular momentum of J equals 30. So this would be correspond to angular momentum of Z component 30. That's a 2 mod 4 cluster. Here's this one right here at 29. That's a minus 1 mod 4 cluster. And then here's the one that we've been looking at, A1, T1, E. And this is actual numbers for a particular spectrum of silane, tetrafluorosilane. And these splittings are 2 to 1. It's E with T1 in the middle and A1 high, just like we were just looking at a minute ago there. And it corresponds to a cluster in this spectrum right there. And this is a energy surface that we'll talk about later on for angular momentum. And that's something we're going to start next week and go like mad through it. Okay. Now all of these things correspond to different pieces of this table, the C4 table. So there's an A1, T1, E, every 4 things. Every one of these things, I showed this a little bit before, A1, T1, E. Clusters. And then the next one is T1, T2. There. There are twice as many of those because both odd and the 2 odds, 1 mod 4 and 3 mod 3, are both consisting of just the T1 and the T2. And then that one that we looked at that was 2 mod 4, 30 is 2 mod 4. It has an A2, E, and T2. In it, and you see that in this spectrum, the next level here, 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 and so forth. 74, 78, 82, 86, you see. And then 88 is divisible by 4, so the 0 mod 4 cluster shows up on the outskirts of this. Now, the other side of this spectrum corresponds to valleys that are 3-fold symmetric. There you get some really amazing clusters, and that's what was shown in this slide a little bit. They just they're not as prevalent. They're not as much phase space for them. But you can jimmy this thing and make any sort of phase space you want. And when you do, you get some amazing clusters, including these giants here that consist of C2 clusters. And we looked at a couple of tables that had that, and we'll do that, a little bit more of that on tomorrow. I'm sorry, tomorrow. The next lecture is Thursday. Okay? Any questions? This is a heck of a lot of stuff. I'm fully aware of that. But the idea is to take that heck of a lot of stuff and make order out of it. Make it so it works for you. And that's what we're really beginning to do now. And after we look at the off-diagonal projection operators, you'll see how they all get together in a very simple formula, where you can specify all the parameters that are active, say what the parameters do. Parameters that we showed just changed eigenvalues. They didn't change the eigenvectors. With off-diagonal projection operators, then the possibility of changing the eigenvectors from one local symmetry to another, or just something in between a particular local symmetry, all of that's controllable now. We can visualize that. So we can take a model of some crazy thing that's going on in a molecule, or, and this is the hope, we can take something crazy that's going on in graphene or in a three-dimensional solid and make a map of it by mapping all of the positions in either reciprocal space or real space with group operator, and each group operator's parameter for a off-diagonal matrix element. There's some sort of tunneling parameter, you say. So the group's doing everything. The group knows all of the possibilities in a given model. Now this model right here has, in all, 24 parameters. We're only using a little tiny, actually 2. We're making 2 parameters out of that for this particular thing.
And real to boot.
That's right. That's right. And in fact, you can decide whether you're going to have the parameters involved in something that's complex, which means a moving wave, or whether you're going to restrict your local symmetry to say, no, I don't want any moving waves, I just want standing waves. And I want them here, here, and here.
Can you use that same trick to say computation? Say you've done your analysis and you have your projectors, and those conjugates are indeed contain imaginary numbers.
Mm-hmm.
Doing the symmetrizations, adding and subtracting of those, you eliminate the imaginary component. So then would you not be able to project your real Hamiltonian using real projection?
Well, that's something that you can always do, is after you've been given, say, a moving wave like we got for 2 components, and then a standing wave showed up too, all of them had local symmetry 0, 4. I am then free, since they were degenerate, to take combinations of those and not change the eigenvalues. But I am, when I do that, taking myself to a different kind of subgroup chain. Instead of ending on a C4, I'll be ending on a D2 then. I'll getting something that has D2 symmetry. It lost its circulation, its C-type symmetry, but it picks up a bilateral symmetry, a B-type symmetry in addition to the A-type, and that gives me standing waves as my eigenvectors. Now once you've done that, once you've decided I want to do a little transformation of one of the irreducible representations to something else, do it to all of them. You see, you don't have to go back and say, okay, I've got my local symmetry D2, I'm going to use the projection operators, I'm going to work out a sum to get all the projection operators in that chain. No, you go directly to that chain by doing a transformation of the Ds. you see, which is, you know, a few minutes work. Going all the way around is a lot more work. And there are a lot of different paths, as you saw, just for these 32 groups. Start going to higher dimensions or into solid space groups, the number of paths is daunting. So you want to be able to have control of that after you've done the problem once. Then you can walk around to those different subgroup chains just by doing a similar transformation of the D-coefficient matrices. So if you have something that's given you a Hamiltonian that's got off-diagonal components in some submatrix, you can just say, oh, well, if it's 2 by 2, I immediately write down an eigen solution to it, or 3 by 3 you probably do by hand. Then do it to all the D matrices too. See what subgroup chain you brought yourself to. You see the freedom to have all of these different equivalent irreducible representations is the freedom of nature. It's mirroring all of the different possible symmetries, stops there are in between states that have no symmetry at all that you can see. Usually there's something hidden, and that's fun too when you discover that, but it's very easy to make something that has no symmetry at all. All I have to do is transfer all my waves so that they're rotated by 17 degrees. It won't hurt my eigenvalues because they were degenerate. But what if they weren't? Then it would hurt. It would pay energy. It would pay energy to do that transformation.
Which, if you were dealing with the T, that since it had that squirrely, complex scalar,
yes,
you would bump your head.
Basically, you take a moving wave here and add it to the moving wave here. That's like adding e to the I kx, e to the minus I kx. You get a cosine kx. Then I would go ahead the same thing with left and right, subtract, I get a sine. So getting cosine and sine standing waves out of moving waves is something we've talked about with respect to cyclic symmetry. Well, it happens again and again here. If you end on a cyclic subgroup, you're always free to try that to see if it's still an eigenstate. Now, if the physics has put a magnetic field in there so that you have axial vector driving the thing, that's a vector that turns, has chirality, well, taking a linear combination of right and left is going to be beating, right? That's not going to be an eigenstate. But if you can turn that chirality off so that they come down, then why use left and right? Use x and y, you see. It costs me no energy to get the current going if there's a degeneracy. But it will cost me energy if there's a Zeeman splitting. And all of this stuff in the context of these pretty complicated things is really nice to have the group theory on your side. The problem is the pest, not the grouping. Yeah. Okay.